To begin the discussion of single slit interference, I want to remind us of what we did for double slit interference and write the result up in this corner just to keep our memory on it. So we found that in double slit interference, the path difference between the two slits to a point on the screen gave bright spots when the angle obeyed this relationship. We had d sine of theta equals m lambda, where d sine of theta was the path difference between the two rays, and m lambda was our condition for constructive interference, m being 0 or 1 or 2 or 3, some integer number of wavelengths path difference. Okay, so that's what we used, and we were able to use a small angle approximation to be able to find a position up the screen from the central maxima, calling it y sub m is equal to ml lambda over d, where L was the distance between the slits and the screen. So those are two relationships that we derived before. Okay, so holding those in our memory, let's now talk about single slit. Now, the interesting thing is that when we have a single slit, and if I blow it up and make it look really big, okay, so I'm zoomed way in and seeing the single slit. And I think a whole bunch of photons are coming through here. Well, there's some pretty complicated wave theory that can prove this more mathematically and robustly, but some excellent observations throughout history have shown that we can model a wavefront coming through here, okay, hitting this mark, and every bit along it acts like a source of a round or a circular wavefront. And so this spot right here acts like a diffraction point for a wavefront. So does this one, so does this one, so does this one, all the way down. And I've only drawn a few. Infinitely, there are infinitely many in between. And so I can think about this, everything in between here, as being different sources of diffraction. Okay, so all the photons that are hitting here are actually all diffracting in all directions, and therefore this piece here can interact with this piece, or all the way to this end, and they can then interfere with each other. Okay, so extending the discussion that's left in the text, and again, I encourage you to read the text, we can now say, okay, well, let me look and see what light from this corner of the slit is going to do on a screen that's distant away. So I'll draw that distant. Obviously, again, this we have to pretend that this is really small and this is really big compared to our gap here, our slit width. Okay, but let's go and pick a spot, and let's say, well, what happens when I pick a spot up here on this screen such that the path difference from a photon coming diffracting around this edge of the slit is one wavelength different than the path a photon diffracting on this edge of the slit is. So drawing that perpendicular line, labeling the slit width as A, so this side of the triangle is A, noting that that's theta, the same theta of inclination as before with our double slit. This path difference, what we're saying is we're going to say this is one wavelength. Okay, so this wavelength is A sine of theta. And so we have now a condition on theta, what theta needs to be. But let's see what happens up here. Okay, so looking at this picture, this is one wavelength difference. So this photon ought to be in phase with this photon, and they should be bright. That's what we got for the double slit. But the difference is that I have a bunch of other photons available to interact with these. So let's take a look at one right in the middle. It's going up there too. Okay. Now my question is, what is this length here? I'm going to highlight in bold right there. What is that length right there? How big is it? Okay. This is 0. This one's lambda. This one's halfway across, so it's reasonable to say that's lambda over 2. Okay, it's half lambda. Well, that means that this photon is half a cycle out of phase with this photon. And it could cancel. This one can cancel with that one. So I said, okay, well, I lost a photon. So what? You know, I've got a whole bunch of photons here. Well, let's continue that. Let's go halfway between the half, or a quarter of the way across, and compare that to one that's 3/4 of the way across. Well, if that path difference right there is 1/4, as this was 1/2, and this one's 3/4 of the way down our triangle, so that means this length right here should be 3/4. Well, I have 1/4 and 3/4 of a wavelength. The path difference between this one and this one is also a half. So that one will cancel with that one. I could keep doing that and find out that everything inside here is half a wavelength different than everything inside here. And so I lose this entire band of photons. And likewise, everything inside here is out of phase with everything inside here, and I again lose those entire bands of photons. So when the outer two, the edges of this are in phase, because of the availability of as many photons as I need to span this gap, they all actually cancel out, and I get a dark spot instead of a bright spot. When this was filled with an opaque screen, so I only had light coming from here and here, then I got a bright spot because I didn't have all these ones to cancel them out. But with all those now open and many photons available to interact, I end up with a dark spot for the same condition. Okay, so this gets confusing, but if you remember the physical scenario of where it came about, then we can keep them straight. So this case was for bright spots for double slit, and we end up with the exact same thing, only for dark spots now. Okay, so I like to just refer to the same thing. Now the text likes to just to differentiate and to help clarify the two different models is that they, instead of saying this is D, they call it A, and instead of using an integer or variable M, they use P. I don't like that. I mean, it's like, I want to know, well, what's the condition? Well, I know with single slit, that condition of one wavelength means all these photons are canceling. And with double slit, I don't have those extra photons, so the outer ones are in phase, and so this is constructive. So just remember, you can use the same thing here, and we're going to have for double slit, or two slit, that's for bright spots, or constructive, and for single slit, the same relationship holds for dark spots. Okay. Now generally, when we do have double slit, the width, this D being the distance between the two slits, is usually much larger than the actual slit width. And so you can end up, as I showed in the previous video, you can end up with peaks, or you have these peaks that look like this. Okay. And this is the spacing of these peaks is the double slit effect, and they're smaller because D is bigger. Okay, since D is bigger, these will get smaller. And the single slit is usually quite small. You know, sometimes a third the size, a fourth the size, or more, maybe a tenth the size. In this case, I have drawn these such that the single slit effect reaches a zero. Its first zero is at the fourth zero, or the fourth bright spot for double slit, and we'll do some math a little bit later, but for an example there. But the point being is that the single slit had a small width, making a big space before its first dark spot, whereas the double slit had a bigger spacing between the slits. Therefore, it was a smaller step to get to its first one. In fact, it could get to the fourth one by the time the single slit did, for this example here. I will actually do that example mathematically in the next video. But the important thing I want you to see here is that this relationship is the same because of this criteria, only for one case, with only 2 points of light to use, we get bright spots. The single slit, we have lots that can interfere with each other, giving us a dark spot. Okay, now before moving on to that example, there's one other thing. The peaks, our theory for the double slit, as I mentioned earlier in the previous video, the intensity should be uniform, and it gets dim only because of this single slit envelope. But what's interesting is for the single slit, if we didn't have any of these double slit, this was just one single slit, the side peaks get dimmer. Okay, they get dimmer. So not only is this peak wide, okay, they get dimmer. And it's quite. I want to point out why is that the case. So let's draw another case. Okay, I'm going to have some screen over here. Now let's choose a spot a little bit higher so that this path here is now 3/2 wavelength. So we've moved this up more to reach a spot higher, extending this path difference. So I'm not going to draw the whole thing, but I'm going to draw it like this. And there's my cross piece. It's still A. Okay, so now this is 3/2 of a wavelength. From here to here, this is the path difference. What's that going to be up there? Before with one wavelength, I got a dark spot. What's going to be up there? Okay, so let's see what happens. If I were to break this into thirds, one right there, one right there, we could see that if this edge is 3/2 of a wavelength, and by the symmetry of these triangles, this one should be one wavelength or 2/2, and this one would be half a wavelength. Okay. Now, if I were to just cover up that piece right there, what's left, the remaining piece right there, is the same as this problem over here. And so I could argue that this is going to cancel with this. But now, this band right here is from one wavelength to 3/2, and so only the edge could cancel, but everything in between, there's nothing in there that is fully canceled by another wavelength, which means this band does make it to the screen. And so before I had, if I were to consider the central beam, all this has come together, everything lines up, I would get all of this light hitting the screen. But on the first maximum away from the central, only 1/3 of the light is making it to the screen. So it's actually going to be dimmer. So again, to avoid this complication that I drew over here with the double slit and single slit, if this was just a single slit, I would get a dimmer patch, and then a brighter central maxima, and then a dimmer side one. And so because of this peak is dimmer than this one. The next one would be even dimmer. We could extend this argument up further. You get just a smaller and smaller section that actually gets to the wall. So you get these dimmer and dimmer side peaks. Okay? And so that's something to note. That's the difference between them. You can tell single slit from double slit, and that the side peaks get dimmer. I want to point out why the central peak is a maximum. Okay, sorry, I apologize. Why the central peak is twice as wide as any side peak. All the side peaks are the same width, but the central one is twice as wide. And the reason is when we went from m equals 0 here, well, that is symmetric, okay, which means all the light interferes constructively. And then we move to just the first wavelength. We get to the first spot, and that is now a dark spot where we have one wavelength difference. And so we move from a central maximum to a dark spot on either side. And then when we go one more wavelength, that gets us back to another dark spot. So these ones are very similar in terms of their width as these double slit equal width ones. But the central one is twice as wide because from going from a maximum, it goes to a minimum at the criteria instead of another maximum. For the double slit, it would have had to get to a maximum again and a maximum again. And so the double slit's all equal spacing. Single slit has a maximum that's twice as wide. So the intensity decreasing and the central maximum that's twice as wide as the all other maximum are the two defining features that tell you it's a single slit rather than a double slit. And then if you see this effect where you see lots of equal spaced ones but they get dimmer and then brighter and then dimmer, that is the effect of both double and single slit being shown together. And if you see them that they're all uniform all the way across, that's a theoretical double slit, because we can't actually create that unless we were somehow able to create crazy small slits that are a decent spacing apart.